Hello, I'm Walker Khan, and this is Lab 5, Magnetic Braking with Faraday. The purpose of this lab is to observe and record the fall time of a magnet within an aluminum foil tube. We then want to compare our physical results to a simulation that utilizes relevant physics principles. Such principles include Faraday's law, which calculates the current on each pole, rings for this scenario, of the falling magnet, alongside PHYS law, which calculates the magnetic field, and consequently forces, on each ring. A supporting principle is Newton's second law of motion, which states the force is the product of mass and acceleration. To the left is critical data required for the simulation calculations. The magnetic dipole moment derived from Lab 3's results, as both experiments utilize the same bar magnet. The table on the right contains the drop times of the magnet through the aluminum foil tube. Here's a glow script code that simulates our falling magnet. Some important aspects include the variables required for both Faraday's and PHYS law, the function that carries out PHYS law calculations, and the same for Faraday's law, which helps determine magnetic flux. Shown afterward is a loop that iterates these calculations concerning a time interval. Our code concludes by printing the total time our bar magnet spent in the aluminum foil tube, alongside the two aforementioned laws. To the left is the executed glow script code. The red ring represents a clockwise motion of the current, provided by the falling magnet, whereas the blue ring represents counterclockwise. To the right is the final output of the simulation, which states that the magnet spends a total of 1.368 seconds in the aluminum foil tube. We wanted to compare this to the average drop time from earlier in the lab, which we found to be 1.52 seconds. In terms of the outputted graph, one observation to point out is the brief moment of velocity is constant, which according to Newton's second law of motion, indicates that our F net is equal to 0 during this time interval. To reiterate, our simulation yields us a fall time of 1.368 seconds, whereas the average fall time from our physical observation is 1.52 seconds, approximately 11% error. What if the resistivity of the conductors were reduced as close as possible to 0? The induced current and magnetic force acting on our bar magnet will increase. As a result, the magnetic falls slower. What if holes or slots were cut into the tube? Resistance within the tube will increase, consequently inhibiting the induced current and magnetic force within our system, resulting in the magnet falling faster. Thanks for watching.